players are A, B, C, D, E, F, G, H. Right. So suppose that these are their name. Right? And how to make the table? So names. Right. So you have there are 8 people. And there are the same people. Right. And you know that, so for example, A and B will play one game, right? So we just put a circle here.
Wait, does A plays B this technically the same thing as B plays A?
You're right. So basically, if A plays a game with B, then that's exactly the same game where B will play the game with A, right? So let me complete the table first. All right, so how to show this in the table? So basically, if A plays a game with B, then we can put a circle here, right? Then we don't have to put a circle here because basically they represent the same game. Okay, so let me erase that. Okay. And if B plays a game with C, then we can put a circle here. Okay. So, but we don't have to put the circle here because, so basically this one and this one are the same games.
And there's a total of 56 games.
Good. So if we complete this table, so you can see that we'll fill out all of those spots.
And then you have to divide by 2, which equals to 28.
Okay, so let's count them one by one. So you can see that because A will not play the game with him or herself, right? And B will not play the game with him or herself, right? So all of the dots are below the diagonal, right? So if you consider this as the diagonal of the table, so you can see that all of the circles are below the diagonal. Or equivalently, you can put all of the circles above the diagonal, right? So they are equivalent. I mean, you can also put them there. And so on, but you only choose one of them, right? Because we only count the game once. So if you put the both of the circle and the crosses, then that means you count one game twice, right? So that's why we either use the circles or either count the crosses only. Right, so let me erase them. Now what we need to do is to count the total number of the circles. Right? So you can see that in the first column, there are 7 circles, then 6, 5, 4, 3, 2, and 1. So basically, we just need to add them together. Right? So we just need to do 7 plus 6 plus 5 plus 4, and so on plus 1. Then, so we know that this can be calculated by using a formula. So we add the first term and last term times the number of the terms divided by 2. So that's 28. So that means there are 28 games. So this is the first method, right? So we can count the number of circles in the table. So from the table, you can see that we only count, so how to count each game only once. And from the table, you can see there is a structure, right? So basically, so the number of games in the first column is one more than the number of games in the second column, and the number of the games in the second column is one more than the number of games in the third column, and so on. So, or we can use a diagram. So we just put the 8 people in this way. And we know that, so everyone will play one game to anyone else, right? So A will play one game with B, one game with C, one game with D, one game with E, one game with F, one game with G, and one game with H. And B will do the same thing. So B will play one game with A, then one game with C, then D, E, F, G, and H. And then C will play one game with B, then one game with D, E, F, G, H, and A. And A. So if you continue to do this, you can see that so every game will be counted twice. Right? I think that will be easier to, that will be more clear if there are less people. Right? So for example, if there are only 4 people, then let's do the same thing. Right? Then B with A, D, and so C will play game with B, D, and A. And D will play game with A, B, and C. Right. So you can, from this diagram, you can see that so every game is counted twice. Right. So from this diagram, we can easily count the number of games. So that will be, because there are 4 people. So in the smaller diagram, because there are 4 people, and every player will play 3 games. So we multiply it by 3, because every game is counted twice, then we divide it by 2. Right? So there are 6 games. And from the graph, we can see that this is correct, because there are 1, 2, 3, 4, 5, 6 games. Then let's go back to this big diagram. So we want to apply the same formula to calculate that. So basically there are 8 people, and everyone will play 7 games. Then every game is counted twice, so we divide it by 2. So there are 28 games. Right, so this is the second method to calculate that. And you can see that we get the same number if we compare it with the first method. Actually, there are many methods. And I think, so these 2 methods are the most clear method, because you can see what happened exactly. All right, so any questions so far? So actually, this kind of problem is called, what is that? Combination. Sorry, so I forgot the name. Yep. So this type of problem is called combination. Well, so for this kind of problem, so later you will see that we can solve for all of this kind of problems by a uniform formula, right? So it's denoted by C, right? And CMN, right? So this is the notation. So basically the capital character C denotes the combination, and the M is the total number in the set. So for example, in this case, the total number is 8. And n is a number of choosing. So basically, for example, you want to pick 3 from 8. So then we just need to put a 3 on the top. So number of picking. So later we'll see how to calculate such a term. All right. So for example, in this case, so never mind. So let's look at the second problem, 14.18. Well, so in this case, we want to generalize the formula we got in the previous problem. Again, that's the same tournament, and then the same rule. Then we want to find the formula for the number of matches that will be held during an 8-person round-robin tennis tournament. So where n is greater than 2. I believe this is n. Right, so we want to know if there are n people. So n can be any number greater than or equal to 2. Right? So for example, 4 people, 5 people, or 10 people, or 100 people. Then what's the formula should we use in this case? So if we review the two methods we used in the previous problem, we can see that, so if we use this one, so basically we should do 1 plus 2 and so on, and plus n minus 1, right? So because if you look at the most number, so because in that case there were 8 people, then the most number is 7, which is n minus 1. Right? So basically we just need to count the sum from 1 to n minus 1. Again, so we can calculate that by the formula. So that's n minus 1 times n minus 1 plus 1, then over 2. So if you simplify it, we'll get n times n minus 1 over 2. So that's the formula we got from by using the table. Then if we use the diagram, then we can see that it's calculated by this formula, right? So basically, the first number is the number of people, right? So that's n. Then times the number of games. So for each player. Then divided by 2. So basically, there are n people in the game. Then every player will play n minus 1 games with the other n minus 1 players. Then we divide the total number by 2. So you can see that we get the same formula, we get the same answer by using the two methods. So both of them are n times n minus 1 over 2. All right, so any questions so far? Well, so there's a concept. So we can sometimes use counting explanations to do algebraic relationship. Yep, so, well, this is true, right? So especially when you do a type of problems at the first time, it's recommended to count them one by one, right? Because we don't know what happens in this type of problem, right? So we should try each of the situations, just go through all of the cases and see what happens. So you can also follow what I did. So for example, if there are too many numbers, for example, you think A is too large, you can just try a smaller number. So for example, you can try a 3-person game or 4-person game or 5-person game where you can see what happens exactly, right? Then you can just enlarge that number step by step. Then you can just, if, for example, you want to, for example, the here is 100, right? But you only tried like 3, 4, 5. That's not bad because you can conclude some rules from those small number cases. Then you can try if there is any way to conclude such a formula or such a rule, right? So for example, we get a formula like this from those small number cases, like 4, 5, 6, 7, 8. Then we can generalize it to those large number cases, or say any number. Right? So no matter there are 100 players or 200 players or 1,000 players, so they are exactly the same formula. Then so that's why it's very useful to consider some small number cases. Then you can just generalize it. All right. Then let's look at the next problem, 14.19. So there are 5 women and 4 men, and they are in a party. So if each person shakes hands with each other person, then how many total shake hands are there? So actually this is very similar to the previous 2 problems. So you can still
10?
name 10. So why is that?
Because 5 times 4 equals to 20. 20 divided by 2 equals to 10.
Very good. So basically, David used the formula we got in the previous problems, right? So because there are 5 people and everyone will shake hand 4 times, right? Because
are there 9 people?
I'm sorry?
Aren't there 9 people?
You're right. So there are 9 people. So Davey, so why is there 10 shake hands?
Because, for example, I'm gonna try it, okay?
Okay,
If
so
A shakes hands with B, then it would basically be the same thing as B shake hands with A. So when you get 4 times 5, you have to divide by 2.
but
Because
how many
it's
people is
overcounted.
there?
So why is it 4 times 5?
Yeah, so why is that's 4 times 5? So how many people is there? How many people there?
9. Wait, no.
So what should be? Because there are 9 people, right?
36.
Good. So can you tell me your formula?
So if it's only 9 people there, then 9 times 8 equals to 72. And
Okay.
72 divided by 2 equals to 36.
Good. So very good. So basically, if we apply the formula we got in the previous problems, so we just have 9 times 8 over 2, right? Because there are 9 people and everyone will shake hands 8 times. And because every shake will be counted twice, so we divide the total number by 2. Good. Then let's see the problem B. So there is a restriction to the handshaking. So if no 2 men shake hands, but each woman shake hands with each other person, then how many total handshakes are there?
When I do it,
Who is talking?
William,
Okay, William, can you do it?
it's
By the way, can you turn on your camera?
21.
Okay, so why is that?
Because 7 times 6 equals 42, and then divided by 2 equals 21.
Why is 7 times 6?
And because two men didn't go to the party. No, like they didn't shake hands.
Let me see. So if no two men shake hands, so that means, let me explain the problem first. So basically, for example, there are 5 women. Let me call them A, B, C, D, E, and the 4 men, F, G, H, I. Right. So 5 women and the 4 men. So what does that mean? So this time it says if no two men shake hands. So that means F will not shake hands with G. So F will not shake hands with H, F will not shake hands with I, but F will shake hands with A, B, C, D, E. So F will still shake hands with the women. So G is the same. So G will not shake hands with F, G will not shake hands with H, G will not shake hands with I, but G will shake hands with A, B, C, D, E.
Yeah, then it's 20.
Good. So basically, the 4 men will shake hands 20 times. Right? But so there will be 20 shake hands. So these are shake hands for where the men will do. How about the women? So let's continue to think about this problem. So even though, so for example, here we have counted the number where the number where the man will shake with women. What if, so how about those shake hands between the women, right? So for example, so it says, but each woman shake hands with each other person. So that means A will shake hands with B, A will shake hands with C, A will shake hands with D, and A will shake hands with E. The same, so B will shake hands with A, and C, and D, and E. And C will shake hands with A, B, D, E, and the D will shake hands with A, B, C, E, and E will shake hands with A, B, C, D. So that's why we need to add something, right? So basically, that's the number of shake hands between the women, between 2 women, right? So can anyone tell me that number?
7.
So why is that? Well, so actually this question go back to the question A.
Oh no,
Right.
no, it's 9.
Okay, so can you tell me how did you calculate that? So that means there are 5 people, there are 5 women, then they shake hands with each other. So what's the total number of shake hands between the women? So there are 5 women, right? So every woman will shake hands 4 times with the other women. And then because each shake hands is counted twice, so we divide it by 2. So this equals 10, right? So the second part is 5 times 4 over 2. So there are 10 handshakes. So finally, if we add them together, then there are 30 handshakes. So any questions so far? Well, so you can see that. So actually, there is one way to check if the answer of the question be reasonable or not. Right? So basically, this number should be less than 36. Why is that? Because in the question A, well, so 36 is the answer of the question A. So in the question A, there is no any restriction, right? So basically, just like I will shake hands with everyone here, and Victor will do the same thing, and Anna will do the same thing, David will do the same thing, and William will do the same thing, and so on, right? But so basically, there will be more handshakes than the question B, right? Because in the question B, there is one more restriction. So basically that's saying I cannot shake hands with Victor, nor Davy, nor William, because all of us are men, right? So I can only shake hands with Anna and the other girls. And this is true, also true for Victor, for Davy, for William, for Ethan, and so on. So for all of the boy students and me, right? So that means there are less handshakes, right? Because I cannot do that handshake with some people. So that's why this number must be less than the total number. So basically this provides another idea to calculate to figure out the question B. So basically I just need to figure out so how many handshakes are reduced. So basically how many handshakes are prohibited. So for example, basically what we cannot do are the handshakes between the men. Right? So basically, so F cannot shake with G, no F, no H, no I. So G cannot shake with F, H, and I. And H cannot shake with F, G, and I. So let's see how many handshakes there. So there are 1, 2, 3, 4, 5, 6. Right? So the number here is 6. Then we get the same number 30. Right? So you can see that this is the correct answer. So for all of the counting problems, you can always use, so you can use any of those two ideas to figure out the answer. Right? So you can either find the number from just like, how to say that? So from the positive side, like, so you can just count like how many situations are covered. So how many cases are covered, and then count the number for each of those cases and add them together. Or you can go back from the other side. So you can find the total number first and see how many numbers are not included. So how many are not covered, and then you subtract that from the total number. So both of them are available for the counting problems. And it depends. So sometimes the first method is easier, but in sometimes the second one is easier. Right? So it depends on the problem. Okay, so any questions so far? Well, so there is a warning. So when dividing by 2 in a counting problem, to correct for counting each item twice. So make sure you really were counting each item twice. Well, yeah, so definitely. So it's recommended to have a table or diagram before you're counting, right? Because it will tell you what happens exactly. So if you just imagine it in your brain, so sometimes it's confusing, right? Because sometimes you will miss something, but sometimes you count something more. So it's always recommended to have a diagram for a counting problem. So diagram recommended. All right, then let's look at the problem 14.20. Well, so there are 5 questions. Let's go through them one by one. Question A, so how many diagonals does a triangle have? Because the 5 questions are geometrical, so it's natural to have the diagrams, right? So if we look at a triangle, so we can see that there's no way to have a diagram, have a diagonal, right? Then, so how many, so 0. Then for question B, so how many diagonals have a quadrilateral have? So for a quadrilateral, so basically we just need to connect, if we connect those 2 points, and if we connect those 2 points, so there will be 2 diagonals. Anything else? No, so that's all. Then let's go look at the question C. So what if there's a pentagon? So basically it's saying that there are, it has 5 sides and 5 vertices. Then, so let's see how to have a diagonal. So if we connect those 2 points, that will be one of the diagonal. Then if we connect those 2, this is another diagonal. Then, so this, then this is the 3rd one, and the 4th one, and then this is the 5th one. So anything else? That's it, right? So there are only 5 diagonals. Well, so even though they're basically, we just follow the questions in this problem, but if the problem asks you about the polygons directly, it's also recommended to follow this pattern, right? So we also start from the simplest case, a triangle, then move to the next case, a quadrilateral, then move to the next case, a pentagon, and then move to the next case, a hexagon, and so on, until you find the rule or find the formula. Right? Then let's try concluding something from those simple cases. Well, so there's question D. So there is a hexagon. So let's see how many diagonals there. So if I start from this vertex, then 1, 2, 3. Then if I start from this vertex, then 1, 2, 3. Then if we start from the next vertex here, so this has been counted, then 1, 2. Then if we start from the next vertex, so all of the 3, so there's 1. And then if we start from the next vertex, so all of them has been counted. Right? So all of 1, 2, and 3. So 1, 2, and 3. All right. So let's see how many diagonals there. So we have, there are 3 yellow one, and then 3 red one, and then 2 green one, and 1 blue one. So there are 9 diagonals. All right, so then we want to conclude something from the 4 simple cases. So 0, 2, 5, 9. Then let's recall how did we calculate them? So for a triangle, there's no way to have a diagonal, right? So that means to have a diagonal, there must be 4 or more vertices. So actually you can see this by numbering the vertices. Right? So for example, 1, 2, 3, and then 1, 2, 3, 4, then 1, 2, 3, 4, 5. So you can see that to have a diagonal, so you have to connect 1 and 3, and 2 and 4. So basically, there must be a number between, there at least one number between the number of the two vertexes, right? Because if you connect number 1 and number 2, it's not a diagonal, it's a side, right? If you connect number 2 or 3, it's another side, it's not a diagonal. If you connect number 3 and number 4, it's a side as well, right? So it's not a diagonal neither. So that's what. So to have a diagonal, so there must be at least one number between the two vertexes. Right? So if you check the next one, so that's the same thing, right? So you see 1, 3, that's the first diagonal. 1, 4 is the second one. Then 1, 5 is not, right? Because 1 is adjacent to number 5. Then 2, 4 is the next diagonal. Then 2, 5 is the fourth diagonal. But we cannot do 2, 1 because 2 and 1 are so they are together. Right? Then for number 3, so 3 and 5 is the last diagonal. Right? And you can see that, so when we count them, to make sure that any diagonal will not be counted twice. So basically, we require the second vertex, the number of the second vertex is greater than the first vertex. So for example, 3 is greater than 1, 2 is greater than 4, and here 4 is greater than 1. So 4 is greater than 2, 5 is greater than 2, and 3 is greater than 5. So why is that? Because if the first number of the vertex can be greater than the second one, so for example, if I would do 4, 2, so even though 4, 2 is a diagonal, right? So this one is a diagonal, but it has been counted, right? So it's repeated. So this is a repeated one. So that's why we don't want this when we count the number, right? So that's why we require that the second number of the vertex is greater than the first number of the vertex, like this. Then, so in the next case, that's the same thing. So 1, 2, 3, 4, 5, 6, right? So there are 6 vertexes. So if we follow this rule, so we can have the list easily, right? So from the vertex 1, so we can have 1, 3, 1, 4, 1, 5, and that's it, right? Because 1, 6 is next to 1, right? Then we have 2, 4, 2, 5, 2, 6. Then 3, 5, 3, 6. Then 4, 6. Then if you add them together, there are 3, 3, 2, and 1. So their sum is 9. Then if we follow this pattern, we can easily see how many diagonals for like 7-side polygon. Okay. So it should have a name, but I forgot that name, so I'm sorry about that. So if there are 7 sides, or say 7 vertexes, then we can have the list easily. So we have 1, 2, 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, and 2, 2, 4, 2, 2, 5, 2, 2, 6, 2, 2, 7, then 3, 2, 5, 3, 2, 3, 2, 6, 3, 2, 7, and then 4, 2, 6, 4 to 7, and then 5 to 7. So this is a list for 7-side polygon. Like, so how from this list we can easily see that how many how many diagonals there. Okay. So then the total number is 4 plus 4 plus 3 plus 2 plus 1. So this is 14. Then from here, I mean, from those cases, we can conclude the formula to calculate the number. So basically, you can see that if there are 3 sides, right? So sorry, if there are 5 sides, so we calculate it in this way. Oh no. So if there are 3 sides, sorry, if there are 5 sides, so we calculate by 2 plus 2 plus 1. Right, so for this one, so we calculate by 1 plus 1. And if there are 6 sides, we calculate it by this one. And if there are 7 sides, we calculate it by this one. Right. So basically that's equal to, we can guess that. So that's equal to n minus 3. Right, so that's the first number here. Then plus n minus 3 plus n minus 4 and so on, and plus 2 plus 1. Right. So that's the term here. So finally, we just need to calculate their sum. So that's equal to, so n minus 3 plus, so for this part, we can use the formula, which is equal to n minus 3 plus 1 times n minus 3 over 2. And then we can find this. So we can factor n minus 3 out. Then that will be 1 plus n minus 2 over 2. So if we combine them together, so this will be n over 2, right? So if you put them together, so this is n over 2, then the answer will be n minus 3 times n over 2. Right, so that's the answer. So any questions so far? Well, so if I were in a contest or in an exam, so I will figure out the problem in this way. Right? So even if there is no question A, no question B, question C, no question D, if you see the question E directly, it's also recommended to figure out this problem in this way. Right? Because by solving for those simple cases, then you can know the rule, or say you can know the formula. Right? So in this problem, we can see that we just conclude the formula by following those simple cases, from triangle to quadrilateral or pentagon, hexagon, and so on. And you can try 1 more or 2 more to check if this rule is correct or not. Right? So for example, we check if that's correct for a 7-side polygon. If you want, you can try 1 more. So you can try if this is true for 8-side polygon or 9-side polygon. All right, so that's the problem 14.20. Any questions so far? Okay. Well, so you may think this method is not smart, right? So I believe there are some more smart ways to figure out the problem. But so when you meet complicated problems, some of the smart methods may not work. Right? So even though this one is not the best, right? So this method is not the best because you have to try some simple cases. You have to go through some simple cases, but it works. Right? I believe it works for most of the counting problems. So that's why I recommend it here. And I also recommend you to to try this method, even though it's not the best one. Right? So in my opinion, so this is a basic method, right? So when other methods do not work, you can always try this, right? So you can always start from the simple cases and conclude the rule or the formula and see if it works or not. But it's also recommended to read or go through those better methods, right? Or it's recommended, for example, go through the textbook or go through some like websites or someone else and discuss to see if there are some other smarter ways to do them. Because so the more methods you see, so the more methods you can understand, and then the more situations you can face. So it's like if you have more tools, so you can do more things. But before that, you have to have a basic tool, right? So because that basic tool can do something, can deal with most of the situations. All right. So then let's look at the problem 14.21. So the phases of, so from this problem, we're going to the next section. So in the new section, we will discuss a concept which is called probability. Do you know this word? Have you heard of this word probability? Okay, so some of you guys did. So basically, the probability is a number to describe how likely an event will happen. So basically that means if the probability of an event is high, that means it's more likely to happen. If the probability is small, so that means it's unlikely to happen. However, so there's a gap between the probability and the real life. So for example, if you so for example, when you play a game, right? So the game tell you, well, so it's 95% to lose, but there's 5% chance to win. So for example, if there's a game, it says there's 95% to lose, but there's 5% chance to win. So you cannot say, well, you will lose after the game, right? Because it's still possible to win, even though the probability is low. So that's the gap between the probability and the real life, because the low probability does not mean that that event will not happen, right? It could happen, but it's not likely to happen. So here, so that's why the probability only describes the likelihood. So how likely one thing will happen or not. All right, so let's look at the problem 14.21. So, so you can see the probability problems for those dice or the card games frequently. Okay. So the faces of a fair 6-sided die are numbered 1, 2, 3, 4, 5, 6. So fair means that each side is equally likely to be rolled. Then what's the probability that when the die is rolled, a 2 is facing up? So that means there's a,
6.
good. So that's 1 over 6. Right? So there's a die, and it has 6 sides, right? So we know that. So that's the back one is number 4, the left one number 5, and
Wait,
the
isn't
bottom
like
one is number
if you
6.
roll 2 die and getting doubles, isn't that still 1/6?
So later you will see another problem about your question. Right? So we will talk about that later. And all right, so in this case, it's pretty easy. Right? So the answer is 1 over 6. Because there are 6 sides, and every side is equally likely to be rolled. So that's why the probability for each side to be rolled is 1 over 6. Right? So we just divide the total number. So here it should not be called total number. So the 1 here, so actually that's, you can consider it as 100%. So basically, so by the way, so when we discuss the probability, it has 2 bounds, right? So the lower bound is 0, right? So any probability must be greater than or equal to 0, because 0 probability means it will never happen. So that's the best, that's the worst case, right? So if something will never happen, so that's the lowest, or say the worst probability, right? That will be 0. So 0 is the lower bound. The upper bound is 100% or just 1, right? So 100% means it must happen, right? So that's the best case, right? So it cannot be more than a 100% chance to happen. Right? So that's why any probability must be greater than or equal to 0%, but less than or equal to 100%. Or in another word, so it must be greater than or equal to 0, but less than or equal to 1. Okay. So here, if we divide 100% by 6, okay, so that means, so all of the 6 events, the probability of happening any one of the 6 events is 100%, right? So if you roll die, so the number you get must be 1 of 1, 2, 3, 4, 5, 6, right? So 0 will never be there, 7 will never be there, so 10 will never be there, right? Because there are only 6 numbers on the die, right? So there are 1, 2, 3, 4, 5, 6. So the number you get must be 1 of 1, 2, 3, 4, 5, 6. So that's why if you combine all of the 6 events together, so it must be 100%. Right? But so now we want to divide them into 6. Why is that? Because every event is equally to happen. Okay? So that's why the probability for any of the event is 1 over 6, or say 100% over 6. So that's why the event of 2 facing up is 1 over 6, or say 100% over 6. Well, so then can you consider the next case? So for example, if this is not a square die, right? So for example, if this is a die like this, and you can see that there are only 4 sides. Right? So 1, 2, and the left side is 3, and the bottom side is 4. Then can you tell me the probability that when the die is rolled, a 1 is facing to us? Well,
what is
so
fair dice?
yes, it's a fair die.
Oh, then 1/4.
Good. So in that case, that will be 1/4. Because, so in this case, so every side is, well, so every side is, what is the name of that triangle? So that's called
Pyramid?
I'm sorry?
Pyramid?
So basically every side is equal for that triangle. It's called equilateral. Anyway, so basically we know that so every side is equal for this die. So then you can try yourself. So you can construct one of them, then you can see that every side is equally to be rolled. So in this case, because there are only 4 faces, or say there are only four sides, and every side is equally to be rolled, so the probability of one side to be rolled is only 1/4. Because in this case, so 4 events share the 100% probability, right? But in the previous case, the 6 events share the 100% probability. So then we can have the next concept. So if all of the outcomes are equally likely, then the probability of success is the number of success outcomes over the number of possible outcomes. So in the problem 14.21, because the number of success
50% because half of the numbers are odd.
are you talking about the next problem?
Yeah.
Oh, okay. Just one moment. Because in the problem 14.21, so the number of success outcome, so there's only one outcome, which is successful, right? So that's when 2 is facing up, right? Then let's look at the next problem, 14.22. So Davey, can you say it again?
It's 50% because half of the numbers of a die is odd.
So can you tell me the odd numbers?
1, 3, and 5, and the even are 2, 4, and 6.
Good. So because there are only 6 numbers, so 1, 2, 3, 4, 5, 6. And the odd numbers are 1, 3, and 5. So that means no matter you roll a 1 or you roll a 3 or a 5, so all of the 3 outcomes are successful. So all of them are counted as successful. So that's why we calculate this probability. So the numerator equals 3. And the denominator is 6 because, again, there are 6 events, right? So, or say there are totally 6 outcomes, right? So 1, 2, 3, 4, 5, 6. And then if we simplify this, we have 1/2, right? So 1/2, if you rewrite it as a percentage, then that will be 50%. All right, very good. So any questions so far? Well, so then let's look at the next problem, 14.23. So what is the great possible probability for any event? What is the least possible probability for any event?
99 and 1.
Can
Or
that be
is-
great?
Or if you count decimals like 0.00001%, something like that.
So what if something will never happen?
Then it's 0% and 100.
Good. So the greatest one is 100%, right? Or say 1. Right? So that means that event must happen. And the least probability will be 0%, or say 0. So that means that percent will never happen. So when we consider the probability, we have, so even though they are the two special cases, we have to take them into account. Right? So they are also included. So for example, in the problem 14.22, so even though, so what if the problem asks, so what is the probability a 7 faces up? So what is that?
0, because it's not possible for a die to have 7 or a 6-sided die to have 7.
Good. So in this case, the probability will be 0, right? So even though it doesn't make sense to ask that, because 7 is not it's not a number on the die, right? But it is an event, right? So can a 7 face up, or can 8 face up, or can 9 face up? So 8 facing up is an event, right? So that's why we can consider their probability. All right, so there's a notice. So when working on probability problem, if you ever get a probability that's less than 0 or greater than 1, then you've made a mistake. So all probabilities are greater than or equal to 0 and less than or equal to 1. So you can see that even though for this question, so you get a 0 probability, right? So even though 7 is not a number on the die, so if you ask the probability of that event, you'll still get a 0 probability. So it's never a negative probability. Right? So that means any probability must be greater than or equal to 0. So 0 is the least one. Okay? So it cannot be less than 0. But it cannot be greater than 0 neither. Right? So if something happens in 100% chance, so that means that must happen. So, but no one will say that there is 200% chance to happen, unless he or she is kidding. Right? Well, then let's look at the next problem, 14.24. So a standard deck of cards has 52 cards and divide them into 4 suits. So each of which has 13 cards. So 2 of the suits, so heart and diamond, are red, and the other 2, so they are called spades and the clubs, are black. Do you guys play cards? No? Okay. Well, so it's a kind of game. So actually, there are many games involves the cards. Well, so every card is like this, and there are 4 kinds of suits. And so the 2 red cards are called, so one of them is called heart. So it's like this. So there's a heart on the corner, so or 2 or 3 or 4 corners, whatever, like this. And the other red cards is called hearts. Oh, so sorry, diamonds. So it's like this. And each suit contains 13 cards. So this is the heart ace, then heart 2, heart 3, heart 4, and so on. Then heart 10, heart jack, heart queen, and heart king. Right? So there are 13 cards for each suit. And for the diamond, that's the same thing. The first one is diamond ace, then diamond 2, diamond 3, diamond 4, and so on until diamond 10.
But
Then
isn't the probability of this just since half of the deck is like red? That means 26 over 52
No.
times 25 over 51,
Yeah.
which equals to.
Let's talk about the question later. Right? So let me explain the cards first. Well, so the other two suits are black, so they are spades, like this, and club. So the first one is still, they are still the spade ace and club ace. And then spade 2, spade 3, and then spade 10, spade jack, spade queen, and spade king, and so on. All right, so that's why there are totally 52 cards. Right? So because each suit contains 13 cards. Well, so let's look at the question. So the cards in the deck are placed in a random order, so usually by a process called shuffling. So what is the probability that the top two cards are both red? That's interesting. Well, so what did you say, Davey?
So basically, since half of the deck is already red, that means pulling the first red card is half.
Okay, so good. So this is a good start. So basically, we can consider this as a problem we learned last time. So it's like there are two positions. Okay, position 1, I should use boxes. Okay, so first position and the second position. So for the first position, because we have 52 choices, right? So we can so
Also
any card.
26 over 52.
Good. So for the first card, the probability of a red card is 26 over 52, right? Because the total number of choices is 52, and the number of successful outcomes is 26 because we want the first card to be a red card. Right? So that's why it's 26 over 52, which is 1/2. If we simplify it. Then what's the probability of the second place, the second card to be red?
So if one card has been taken from the reds, that means it's 25. Oh, but then there's 25 red cards, but one card is already taken from the deck overall, so that means it's 50 over 51.
Very good. So for the second place, the probability is 25 over 51, because if you check, so you may ask, so why the numerator must be 25? Why cannot be 26? Because to be the successful event, so that means both of the first and second cards are red. So that means if you suppose that event, if you suppose that the event is successful, that means the first card must be a red card, right? So if the first card is a black card, then it fails. So that's why when you calculate the probability of the second place, you have to subtract 1 from the numerator because you suppose that the first card is a red card, right? So that's why there are only 25 red cards left. Good. So the numerator is 25. And then, so for the denominator, that's easy to understand, right? Because you have picked 1 card. So there are only 51 cards. All right. So, and then what's the next step? Should we add or
you should
multiply
them together. And to make that easier, you can just turn the 26 over 52 into half as its most simplified form.
Very good. So the point here is that we should multiply them together, right? Because again, this is a problem which is similar to the ones we learned last time. So here we should use the multiplication. So anyway, we should multiply them together because basically choosing, like picking 2 cards are independent, right? So every time you pick a card and the 2 picks are independent. So that's why we should multiply them together. Well, so the answer will be 25 over
102.
102. Very good. So that's the answer. So any questions so far? Well, so there's another way to check if this is true or not. Right? So we can list all of the possible outcomes, but there are too many. So here, let me only list some of them. So for example, for the first card, well, so if we only classify them by colors, so they could be 2 black, 1 red, and 1 red, 1 black, and 2 reds. Right, so only the 4 situations. So to be 2 blacks, so how many possible outcomes? So basically we pick, so there are 26 times 25 outcomes, right? So for the first black cards, you have 26 choices. For the second black cards, you have 25 choices. Then for the second one, there are 26 times 26 situations, right? Because for the black cards, you have 26 choices. For the red card, you have another 26 choices. Then for the third situation, again, there are 26 times 25, 26. So 26 times 26 different outcomes. Then for the last situation, there are 26 times 25 possible outcomes. So if you want, you can expand each of the situations. So for example, for the first one, so it can be a spade A and a spade 2, right? So that's one outcome. Then spade A and spade 3, and so on. And then the first one is a spade 2. Then the second one is a spade 3, and so on. Right? So if you want, you can list all of them. Well, then, from by listing all of them, you can see that the total number is their product. And the one we want is the last one, right? So the last situation is successful. So that's the number of successful outcomes. Then what's the denominator? So the denominator is 52 times 51, right? basically we just randomly pick 2 cards from a deck of cards. So for the first pick, you have 52 choices. For the second pick, you have 51 choices. So that's the denominator. So then you can see that you will get exactly the same result. Right? So that's also 25 over 102. All right, so any questions so far? Well, so actually the deck of cards is very interesting because people can play many different games by using the cards. Right? But do not play it in a casino, right? Or say, do not play the cards involving money, right? Because that's bad. So you can just, you can play the cards for fun, right? But do not play the cards for money. Well, so let's look at the next problem, 14.25. Suppose that we have 2 fair 6-sided dice numbered from 1 to 6. I think this is what Davey asked at the beginning of this section. Right? So what if there are 2 dice? So if we roll them both, then what is the probability the 2 numbers showing sum to 7? So again, to find the probability, we still go back to that formula. So P equals the number of successful events and the total number of events. Right. So here, if we roll 2 dice, then what happens? So actually you can try listing all of the combinations. So if you do not know how to start, so this is a very good idea. So for example, there are 2 dice. So basically for each of the dice, so the possible outcomes are 1, 2, 3, 4, 5, 6. Right? Then you can just list all of the possible combinations by using the techniques we learned last time. Right? You can either use a grid or a tree. Right? So to use a tree, so we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Then 3, 1, 3, 2, and so on. So the last one will be 6, 6. Right. So this is how we list all of the possible outcomes by a tree. So can anyone tell me the total number of possible outcomes? So how many different combinations? When you
42.
what?
42.
Why is that?
36.
So William, can you explain why is that 42?
No, it's 36.
Good. So it's 36, right? So basically, when you listing all of them, so you can see that so there are 6 groups, right? So and then in each group there are 6 different outcomes. So that's why the total number is 6 times 6, which is 36. Then can anyone tell me how many successful combinations? So if there's
4.
some, is 7. Then can you tell me what are?
I'm pretty sure it's 4.
6.
Wait.
Because you can do 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, and 6 plus 4.
It's 8. There's 6 plus 1.
Is 8 plus 1 included?
I said 6 plus 1. No.
Good. Yeah, so 6 plus 1 is one of the successful situation, right? All right. Now my question is, should we count them twice or once? Right. So if you roll 1 6 and what if you roll 6
You
and
should
1?
count them twice because they're rolled from different dice.
Good. So actually, I think this is the place where this problem is confusing. So actually, so if you number the if you number the dice, so if this is the die number 1, then this is the die number 2. Then we should distinguish 1 6 and 6 1, right? Because that means there are different dice. So number 1 is 6. Number 1 is 1, and number 2 is 6, and number 1 is 6, and number 2 is 1. So there are different situations. But if they are not numbered, so they are just two exactly the same dice, then you roll them. Then what if their positions are switched? You do not know which one is 6 and which one is 1. Then, I mean, there's no way to distinguish the two situations, right? So only if you know which die is number 1 and which die is number 2, then you can distinguish 1 and 6 and the 6 1. So otherwise, there's no way to do that. So I believe in this problem, so we suppose that we distinguish the two dice. So that means this is the number 1 die and this is the number 2 die. Well, so in this case, so we count them twice, right? Because there's different situations. All right. So then can anyone tell me the answer of this question? So then we should put 6 to the numerator, right? Because there are 6 successful outcomes. Then what is the result? What is the answer?
1 over 6.
It's 1 over 6, right?
Yeah.
Good. So the answer is 1 over 6.
It's kind of like just rolling doubles. The chance of you rolling the exact same number is 1 6.
Okay. So if you round it, so what is that? Well, so if we just write it as a percentage, so that's about 13.67%. All right, so any questions so far? So let me ask one more question. So what is the probability of the two numbers shown sum to 1?
0.
0. Very good, because it can never happen. So what is the smallest sum in this case?
2.
2. Very good. So the smallest number is 1 plus 1, right? Then what is the largest possible sum in this case?
12.
12. Very good. So it's 12, right? Because the largest possible number is 6 plus 6, right? So that's 12. So that means only if the number is between 2 and 12, So only if the events where the sum equals 2, 3, 4, 5, or until 12, so the probability is non-zero. Right? So for example, in this case, right? So we are calculating the situation when their sum is 7, then the probability is 1/6. So if you make a chart like this, so let me leave this as a homework. So please make a chart for each of the situations. So now we have known that when the sum equals 7, the probability is 1/6. Right? And when the sum is greater than 13, so the probability will be 0. And when the sum is less than 2, the probability is, so they are also 0. And then can you fill out the others? So like this, 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 this. I should write circles. Right. So can you fill out the table? And then, so if you add them together, so what's the sum? Right. So what is the sum of all of the probabilities? Can you have a guess? So what is the sum of all? Good. So that's 1. All right. So actually, this table is very useful when you study probability because this is called the distribution chart, or say the probability distribution. So once you know this, you can do many things. Right? So for example, you can easily calculate the average